to start off, I'd like to have you do a little short quiz to make sure that you understood the material from the previous lesson. Okay, so I have some shapes and I have a table of values, and I want you to look at the shapes and fill in the table of values based on what you see. And then once you have the table filled in, I want you to write an equation to model the data, and then use your equation to figure out how many squares you'd have in shape number 50. Okay? If you're not quite sure where to start, here's a hint. Look at shape 1, count the squares. There are 3. And by the same token, fill in the number of squares for shape 2 and shape 3, and then see if you see a pattern emerge. Okay? It should be a linear pattern. Okay, so here I filled in the table, and hopefully you got the same thing that I did. And you can see that the number of squares goes up by 2 each time. Each time we increase the shape by 1. So if we're going to use this to make an equation, we should first of all introduce some variables. So if I go capital S for shape and little s for squares, which maybe isn't the best, but we'll try it, then we should be able to write that little s equals 1 plus 2 times capital S. Okay? So that means that if we were to go to shape number 50, then little s would equal 1 plus 2 times 50, or little s would equal 101. Okay? Moving on. This next lesson is about linear and nonlinear relations. So I want you to look at these graphs. And as you may remember from the first lesson, linear relations are ones which have a graph which is represented by a line, a straight line. And you might imagine that a nonlinear then would have a graph that's not a straight line. So immediately you can say that the linear ones are this graph and this graph. Those are linear relations. Whereas the nonlinear is this guy, and this guy. Okay, if you're faced with a table of values, then you're going to go back and do something like we did in the previous lesson. Now, to make things a little bit more concrete, we might look at what are called the first differences. So, for example, in the first table of values, what you're going to do is you're going to take the first differences of the y's. So here, if I just zoom in a bit, you can see that the first differences from here to here, I have to add 5. And then from here to here, I add 5. And from here to here, I add 5. And from here to here, I add 5. So every time I go up, each time x goes up by 1, I add 5 to the y. Okay, so this is the pattern that indicates that this one is, in fact, linear. So this one's linear. We'll use red for linear. Okay, however, if we go to the next one, and we do the same procedure, you can see that the x's are going up by 1 each time, so that's fine. But if we go to the y's, here we see we're adding 6, oops, and then we're adding 2, plus 2, and then here, however, we're subtracting 2, and here we're subtracting 6. So this one doesn't follow the same pattern where we add the same number each time. So this one would be nonlinear. Nonlinear. Okay, then we go to the third one here. And again, we see that the x's are going up by 1 each time, so that's good. On the y's, we see here we're going up by 2, and then up by 4, and then up by 8, and then up by 16. So there is a pattern there, but it's not a linear pattern, because again, we're not going up by the same amount each time. So this one is again nonlinear. When you have your equations, so when you're looking at an algebraic representation and you have an equation, then all you need to do basically is look at your independent variable, which in most cases in math class is your x variable. And when you look at it, you need to see what is the exponent on that variable. So here, for example, in the first one, I just have 2x, y equals 2x plus 5. And although it's not written, it's not explicitly written, there's an exponent on that variable, which is a 1. Mathematicians are kind of lazy, so we don't like to write exponents when we don't have to. So that 1 is implied, and whenever you have a 1, or nothing, because again, we're too lazy to write it a lot of times, that indicates that this is linear. Okay? In the second case, we have an equation where the variable is actually in the exponent. Okay, so it's not quite like the one above, but in this case the x is promoted here. The x is up in the exponent. So that doesn't follow the same pattern. So this one is a nonlinear equation. Nonlinear. And then in the last one, we again can just look at the exponent. So really it's the exponent that tells us everything. In this case, the exponent is not a 1, it's a 2. So because we see the exponent is a 2, then in that case, again, we infer that this is a nonlinear equation. When you have your model, so you might have a model which is represented as an equation, or as a table of values, or as a graph. One of the things we like to do is be able to connect our models. So in other words, go from one representation to another. From now, it's probably easiest if we start with the equation, and then go to the table, and then go to the graph. So the way to do this is you choose x values, and then one at a time you substitute those values into the equation to find the related y value. Now it doesn't really matter which x values you use here, but it's a good idea if you can choose values that are near to 0, at least most of the time. So what I'm going to do in this case is I'm going to choose the numbers -2, -1, 0, 1, and 2. All right, so those are the ones that I'm going to choose, and you'll see why in a moment. Now what I'm going to do is I'm going to go back over here. I'm just going to show you one of these, because I think you kind of get how this goes. If I were to substitute x equals -2 into my equation, then I would have y equals 3 times -2 plus 1. Okay, so I'm going to work exclusively with the right side of my equation. So y equals, now remember your order of operations, 3 times -2 give me -6 plus 1. And then y equals -6 plus 1 is -5. So in my table, I write -5. Okay? Now, now I'll do one more, just so that we kind of get it. Hopefully you get it. But if not, that's okay. So we're going to do one more. This time I'm going to substitute in -1. So if I write y equals 3 times -1 plus 1, y equals -3 plus 1, y equals -2. So -2 goes in there. Now, I won't go through the rest of them, but I will fill in the rest of the table. You can verify that I'm correct here on your own. So the next one would be 1, and then 4, and then 7. Okay, so now I've used my equation to work out my table of values, and now I can take my table of values and plot it on my graph. So I go over to the graph, and I'm just going to plot the points. Get some decent sized points this time. And so, what have I got here? -2, -5. I have a point here. Oy vey. -2, 1, 4, and 7. Kind of like that. Not perfect, but you kind of get the idea. Okay, so that's how we go from an equation to a table to a graph. In this next example, I'm going to show you how to check if when you have a graph, how to know which equation is correct for that graph. So in this case, I'm given a graph, this one, and I want to check to see which one of these equations is the correct one. Now, one thing you might notice is that this graph is nonlinear, right? It's a curve. So as a consequence, I can look at these three equations here and realize, hey, wait a minute, one of these is a linear equation. Well, a linear equation is a line, and it doesn't look like that. So I'm not even going to check that one. That one's gone. Okay, so then I'm left with two more options, and you can see that both of them are nonlinear. The variable on the exponent is a 2, and so therefore we know that one of these two could represent this equation, although not necessarily. So now what I need to do is I need to look at my graph very carefully and try and see if I can figure out a point here on the graph. Now, I want to choose a good point, but it doesn't really matter which point I choose, so long as it's one that lines up nicely with my coordinate system. So, tell you what, let's use this one here. Oops. Let's use this point right here. This is the point 1, 3. Okay, so having chosen that point, I'm going to go back to my equations and see which one of them, if either, 1, 3 satisfies. So in order to do this, you do what's called a left side, right side check. So in this case, oops. So left side, right side check. So left side means look at the left side of your equation. Well, in both cases, it's just y. So the y has a value of 3, because in my point is 1, 3, the y is the x is 1, and y is 3. So in my left side, right side check, the left side is just 3. My right side, on the other hand, I have to look at my equation here, x squared plus 4x minus 2. And I'm going to substitute 1 wherever I see x. So I'm going to have 1 squared plus 4 times 1, subtract 2. And then if I simplify that, 1 squared is 1 plus 4 times 1 plus 4, subtract 2. And simplified even farther, 1 plus 4 is 5, minus 2 is 3. So in this case, the right side is 3. Hey, that's the same as the left side. So this point satisfies the equation. Now, that's not really conclusive. After all, I could have gotten lucky. So what I should do in this case is I should take another point and see that it verifies the equation. How about you do that now, just as a matter of practice? Just pause the video, choose another point on the graph, and see if it satisfies the first equation. Okay, did that work? Well, let's try the same point, 1, 3, in the second equation. And we're going to see if 1, 3 satisfies the third equation, the negative 6x squared minus 2 equation. And you know, it could, after all, we could get lucky, right? But we'll see how it goes. So in this case, again, we're going to set it up the same way. Left side, right side. Now, in this case, the left side is still 3 because 1, 3 is the point that I'm looking at. However, the right side is a little different. The right side is going to be -6 times 1 squared, subtract 2. Okay, now, you need to be a little careful here. Again, your order of operations are important. And so in this case, you're going to do 1 squared. That's going to be the first thing you do. 1 squared, which gives you 1. So this will be -6 times 1 squared, which is just 1, minus 2. Then your next step, you're going to go -6 times 1, which is -6, minus 2, which is -8. Now, in this case, the left side does not equal the right side, right? So we can write that there. Left side does not equal the right side. So because of that, this point, 1, 3, doesn't satisfy my equation. So I can say this equation is not the one represented in my graph. This equation is.